So the Large Hadron Collider essentially is a machine where scientists play games, And what are the games we play? The games are that as a kid, I'm sure you must have been curious to see, for example, what is inside a ball that is making a noise, right? And how did you look inside that? Either you did that with some light on the other side, or you just took a hammer and broke it, right? So what did you do? You gave some energy to that, right? You gave some energy to that ball, you broke it and you looked inside it. And that's precisely what the Large Hadron Collider does for us. We have particle beams. What is the meaning of particle beams? Like bunches of protons that are circulating in clockwise and anti-clockwise directions in two different pipes, beam pipes. And the energy that is given to them is so large because they are accelerated to the speed of light that when they collide, they recreate for a very tiny moment the Big Bang. This apparatus is 27 kilometers in circumference, and it's 100 meters underground. And there, these protons are made to go at these high velocities in two separate beam pipes, clockwise and anti-clockwise, and then at designated points they are made to collide. It's the coldest place on the planet and the largest apparatus on the planet, where we create the hottest material like the Big Bang on the planet as well.
What exactly is it that we are talking about when we refer to dark matter? What exactly is science telling us about the universe? What about some of the interesting stuff we read about when it comes to an alternate universe? Are these theoretical concepts? Is there anything which is realistic in terms of something achievable? Is something quantifiable, something that we can immediately relate with? Or are we talking about science at a level which may be profound, but something which we perhaps cannot relate to in our day-to-day life? A lot of this involves a great deal of science, experiments. A lot of that is taking place at CERN, at the Large Hadron Collider in Switzerland. And Dr. Sharma has been with them for 38 years, is what she was telling me. She is among the senior most Indian scientists now anywhere in the world. And some of the experiments that she is involved in are actually attempting to find an answer to these profound questions. So it's wonderful, ma'am, to have you over here. I know you just about managed to get over here after a tough flight situation, but it's wonderful that you're here. Let me start by asking you, why is it that we need to talk about dark matter, and how is that study profound in terms of human existence at a level?
First of all, thank you very much for bringing me here. And it's a delight to be with compatriots. And in addition, sitting next to you, answering your questions. So questions is what, binds us all. We are so curious. Even as children, we wonder, where did we come from? And of course, we go beyond our own imagination. We start thinking, where we look out at the sky and see, where do we fit in this whole universe? So there are several big bangs, and one of them happens to be the one that created this universe where we live. There could be other universes made out of other kinds of matter that we don't understand. You all have played with Legos, right? So you all know the fundamental building blocks of Legos, correct? So if I give you a set of Legos and I say make an engine, for example, and you make that engine with those Legos, but it doesn't stick together. But let's say that the Legos are magnetic. So you put a strong magnet right in the center and the Legos will just fit where they are supposed to be. And you build this engine, right? Now, we see the universe as an engine built out of all these Legos that we know of. But we do not know what is this magnet that holds everything together. That's the gravitational force of dark matter. And we just call it dark because scientists are very uncreative people. when they don't understand something, they just call it dark. And that's what we are chasing at the Large Hadron Collider.
And how does this actually fundamentally tell us about our own universe and how it was created?
Now, if I say that I give you the building blocks, our Legos of different kinds, which means different kinds of fundamental particles, you all know about the proton, neutron, right? But they are not fundamental. There's still something that makes the protons, and they are the quarks, right? Some of you might know that too. They're the electrons, muons, but then there are just a handful of stable particles that make us. But then there's a plethora of other particles that existed at the time of the Big Bang, 13.8 billion years ago. And how exactly did we come about? All of us were together in that cosmic soup just after the Big Bang, when all the protons that we are made of, and the table chairs, universe, stars, everything that's made up of was made. We were all together in the soup for a fraction of a second before the freeze happened and before the protons were created. So we want to understand this. We want to understand how creation happened, and if at all there are other universes out there with other kinds of particles and other kinds of forces.
And therefore, perhaps the most profound question of all, do we necessarily end our existence where we are right now? Do our particles sort of regenerate elsewhere? Or is this, again, linear, where there is life and there is death? Or is it one constant evolving process across the universe?
I think, first of all, we are not as old as the universe. The Earth and the solar system was created much later. So there's a cycle. One school of thought and philosophy tells us that there's a cycle. Of course, there's a cycle of birth and death and all that also going on in our own culture. But if you look at the way the universe is expanding and collapsing and expanding and collapsing, this could well be a cyclical happening. And we need to understand what is pushing this. And that's also, there's a name to it, which is called dark energy. Simply because the way galaxies are going further from each other, what is pushing them? While the dark matter gravity is pulling it together and keeping it together, there's a force that's pushing it out as well, which is accelerating it as well. So we need to understand all these things, and if we are very lucky, we might find some clues at the Large Hadron Collider.
But tell us about Higgs Boson, just to remind all of us about what it is that you've discovered.
So again, let's go back to the standard model, which means we have particles. Now you all know about electrons, you know about protons and so on. But just a simple question, why is the electron so light and why is the proton so heavy? If there was a tweak to be done, and if they were not exactly the mass they are, we would not be here. So there's some mechanism by which they got mass, and they got exactly the mass that they have, so that, they could come together and make atoms and molecules and nuclei. What was that mechanism? So if I can take the liberty of giving an analogy, so imagine this Pragati Maidan full of people, like us, like all of us together, but loads of people, they're waiting for a big star to arrive. So they all know that they're all talking to each other, but they don't know who's coming. So they're all talking freely to each other, moving from one room to the other and so on. Then suddenly somebody says, name a star. Shah Rukh Khan, okay. Okay. Amitabh Bachchan. I think everybody will relate to him. Okay. So the information comes that Amitabh Bachchan ji will be coming here. Only the information. Nobody has seen him. Nobody has seen any, memo that he is coming. But just that he might be coming, there's going to be a little halchal, right? People will say, oh, which door is he coming? Which gate is he coming? I want to take a picture. I want to take an autograph, right? So there's no physical happening yet, but just the information that there's a star coming will create something over here, a buzz. Suddenly he comes from a gate which was unknown before to us, but he appears at gate number 7. We were queuing at gate number 4 or 3. Then everybody runs to gate number 7. Now, depending on the fan quotient, which means that I love Amitabh Bachchan, right? So I'll be running like this, pushing people behind me and running fast. But there could be people who say, okay, fine, he's coming, it's okay, So I'll be standing behind. So I won't go so fast. So while I'm running so fast, I'm pushing people and I'm acquiring speed and energy and mass. Just because of the knowledge of the star, and B, my fan quotient towards the star. This is the Higgs mechanism. Higgs is the big star, and all particles have different kinds of interactions with the star, so that the more the interaction, the more massive they became. Now, we had to prove this. How can we prove this? That the star really exists. Amitabh Bachchan ji has to appear, and he won't just come. We had to spend billions of dollars for the Large Hadron Collider and the experiments, and then at that certain energy, when we recreate the Big Bang, the Higgs boson might appear. Correct? Because there could be enough energy in those interactions and collisions that the star might appear. And that's what we did in 2012.
Now that you've discovered the Higgs boson, and you've proven that it exists, all that money was well spent. What is the research that you're doing post that? What is it that you've been able to prove? Where are we going with the Large Hadron Collider and everything that it generates?
So first of all, the Higgs boson was just discovered. And what does it tell you? That it's a new entity, like a newborn baby, We do not know how it behaves at all. Does it interact with other particles? Does it interact with itself? Are there other kinds of Higgses? Are there other kind of particles that interact with the Higgses that we can discover? So there's a lot going on. And when we announced the Higgs boson, we had seen barely few, Today it's a Higgs factory, and we are seeing millions, if not billions, of Higgses at the Large Hadron Collider. So we have to study the behavior. Just like when the electron was discovered, and today we all enjoy electricity, we do not know what the Higgs boson is going to bring us. So first of all, scientists are a little bit crazy. They don't really see that what am I going to use the Higgs boson for tomorrow. That's not really the way we are working. But then there are applied scientists who work in the field of medicine, for example, and we heard a lot of examples in the previous session. So I can tell you that right now I am totally fired up to be working in the medtech sector. And why? Because so many of the technologies that are coming out from particle physics are used in the medtech sector. And I can give you a lecture on it, but I will stop and I will not go more into it, except saying that when you take an X-ray, when a bone is broken, this technology is 100 years old, right? Marie Curie started looking at radioactivity. Today, the kind of detectors that we use for the discovery of the Higgs boson, those kind of sensors, we can reduce the dose by 200 times and increase the contrast and resolution by 200 times. So those are the things that fire me up. I think all of you know or should know that the WWW was born at CERN, right? So today WWW is, if I say a trillion clicks per minute, is also not an overstatement, So the relevance in life of science is incredible. While when we were doing the science, we did not imagine what is it that will come out of this. It was only the sharing of data between scientists and large experiments that was needed. And Sir Tim Berners-Lee, when he was a 23-year-old student, wrote the first HTTP page, which is called info.cern.ch. So I feel that personally, science changes dramatically. It has an impact which we do not even know. I could not imagine, when I was growing up in Jhansi and in Varanasi, that one day we would be sitting across oceans and looking at each other and talking to each other. So these are kind of things that we just need to believe in. And I love what I learned as a lesson at CERN, that when we design experiments which are multi-generational, these take 20, 30, 40 years to build, commission, and operate, then we believed 30 years ago that we will have the technology that we will be able to run and operate those machines. So just imagine the sheer force of will that we are going to do that research. And we were hearing about innovation in the previous panel here. That innovation, it's incredible to imagine getting funding to do those kind of experiments, to telling the governments that, we are going to make it. That kind of confidence is what I would love to see in my compatriots. And we are getting there slowly, of course.